Hello, everyone, and welcome to your University of Minnesota. Oh, the font got changed. It's a tiny little, we're getting into the quantum realm here with the School of Physics and Astronomy. We welcome you to another summer of Quirky Quantum Physics. Today's speaker is Professor Fiona Burnell, who is the Edward Yao-Chen Tang Professor of Physics. She received her PhD from Princeton, joined the U of M in 2013. She's received an NSF Career Award, which is highly competitive, and even more competitive, Sloan Fellow, and she is the inaugural Edward Tang Professor. And today, she will talk about her, the background, and I think a little bit of your work, maybe? Okay. On quantum computers. There's one on the side. Everyone will be able to build one in their garage after today's talk. No excuses. And with that, I hand it over to Fiona.
Oh, thanks, Jim. And it's wonderful to see so many people in the room to talk about quantum computers. It's been a really exciting sort of decade in my field, you know, as all of these headlines attest to, because 10 years ago, when I would get on an airplane, you know, and you sit down and you're talking to the person next to you, and they're like, what do you do? And I'd say, oh, you know, I study quantum many-body systems. And people would say, oh, okay. And now I say, I study quantum many-body systems, you know, things that are pretty close to quantum computers. And a lot of people have heard about this, and a lot of people are excited about this. And, you know, it's wonderful to share that excitement with all of you tonight, because I'm very excited about it. So what I want to do in this talk is address basically the following three questions. First of all, if you're going to build a new kind of computer, why would you build a quantum computer specifically? Second of all, what kinds of things can quantum computers do best? And third, you know, why aren't they doing all of these tasks yet? Okay, so that's our kind of questions to keep in your head. And I'm going to dive right in and talk about this first question. I think this is our biggest question for today. Why should I build a quantum computer? And fundamentally, this is a question about how quantum mechanics, how quantum systems are different from their classical counterparts, things that we are used to, like this bottle or a basketball and stuff like that. And in particular, how are they different in ways that are relevant to information storage and processing? And since I'm talking about computers, I'm going to start talking about information and storage and processing in the language of bits. And a classical bit is just a choice, okay? It's like a choice between a fork in the road. I could go left, I'm going to call that 0, or I could go right, and I'm going to call that 1. And unfortunately, if you are a chronically indecisive person like me, when I come to a fork in the road, I have to choose one or the other. I cannot do both of these things at the same time, okay? It's binary. And, you know, if I had an object, like, you know, maybe some baseballs, I could, you know, show that they have to make these kinds of 1 and 0, left and right kind of choices. And I could show that with the following kind of experiment. So like all good parents in my neighborhood, when I was a kid, my parents signed me up for, you know, like t-ball and softball. And have always been completely hopeless at ball sports, okay? And this is relevant for the following experiment. So in the following experiment, what I'm going to do is I'm going to try to pitch softballs. And I've sort of, OK, here I do need my pointer. OK, so I've sort of built a wall here. And the wall has 2 gaps in it, OK? And I'm trying to get, you know, the balls through the gaps. And because my angle of pitching is quite random, OK, about half of the balls are going to go through the left gap, and about half of the balls are going to go through the right gap. Okay? And you can watch those balls go. They're going to go either left or right. And if a ball goes through the left gap, it's going to hit the wall. And, you know, if we sort of pictured where these balls are hitting the walls, most of them are, you know, many of them are hitting right behind this slit. And there's kind of, because the slit is kind of wide, they can get through at a few different angles. And we'd sort of see this blob here behind the left slit, where the balls that had gone through the left slit hit the wall, and we would see a blob through the right slit where the balls that had gone through the right slit hit the wall, okay? So this is what what would happen if I set up this wall with the 2 slits in it, and I threw, me, not a good picture, but me, started throwing balls at this wall. Okay, so that's a classical system. A baseball is kind of a familiar object. We're used to watching them travel around in space. What happens if you do a similar experiment with an electron? Okay? So an electron is a very, very tiny particle, and it is subject to the rules of quantum mechanics. So when I say a quantum particle, a good thing to have in your head is, let's think about these electrons. Okay? In the early 1960s, people started setting up experiments of this type with electrons. So what you do is you get, an electron gun, like these CRT tubes from those old TVs that maybe some of you remember, like I do. And you set up this slit, right? And then behind the slit, it's not in the picture, but behind the slit over here is a screen, okay? And so the electron gets fired out of the gun, it goes through the slits, and it hits the screen. And every time it hits the screen, it makes a white dot, okay? So we start sending electrons through. These electrons are going through one at a time, and they start hitting the screen, and we start to see these dots. And in this picture here, these dots look a lot like me pitching softballs, which is they're kind of all over the place. But as more and more and more electrons get sent through these slits, we start to see a pattern emerge, which is very different from what we saw with the baseballs. We see a pattern that looks kind of wavy, okay? So what is this pattern telling us about how electrons are different from baseballs? To understand that, I want to kind of take a minute to talk about what waviness means. And rather than talk about waviness of electrons, I think it's a lot easier to think about waviness in a context that I hope is familiar to all of you in the summer in Minnesota, which is waves, on our lovely lakes, okay? So here's a picture of what happens if you have the fortune to sit beside a nice calm lake at sunset and you start to throw stones into the lake, right? And you can see that every time you throw a stone, you get this beautiful pattern of ripples, and the ripples are traveling outwards, and those ripples are waves, right? And what is a wave? Well, the water is higher in some places and lower in others. And if you do this experiment, you throw a stone, you make one ripple, you throw another stone, you make another ripple, you can kind of see these ripples collide with each other, right? And if you look carefully at what's happening where the ripples are colliding, the tall parts and the low parts are kind of meeting up and they're just canceling each other out, okay? And so we get these places where there's not a lot of waviness at all. Okay. So here's what would happen if you did something like our double slit experiment on a dock at your favorite Minnesotan lake, okay? So out here, these straight waves, this is the waves that are coming across the lake, the wind is blowing them, they're more or less moving in a straight line, okay? And to do this experiment, you need a kind of unusually shaped dock, which has 3 pieces with 2 holes in them, okay? And when your water waves come to this hole, right, so the water waves can't get through except at the hole, and that makes them make these kind of little round fronts, right? And there's 2 of these little round fronts, and we can see our waves are colliding, our 2 round front waves are colliding, and we get some of this kind of canceling out of the tall and the low parts of the wave, and this canceling out is what we call interference. And now if you take this pattern, okay, of crests and troughs, and you kind of draw a line through it, okay, because that's where our screen would be, right? And we just take a line and we plot like how tall and how low are the waves at this line, you would start to see a pattern that looks something like this, where we have many more bright or tall and dark or low spots than we have slits. We only have 2 slits, but we're going to see this pattern where we have many more, kind of bright and dark spots in this pattern. And that basically is what our electrons are doing. This looks an awful lot like the waviness that we see in our electrons. So what does this waviness mean from the point of view of what an electron is doing differently than what I can do, than what our softballs or baseballs can do? The electron is living by the mantra of Yogi Berra, and I should credit this analogy to my colleague R. Shankar, who I heard it from. So the electron, if it comes to the fork in the road, it does not have to choose to go right or left. It just takes this fork, okay? So the electron, essentially, when it's moving through space, it is free to be a wave, and it's free to do both of those things at the same time. Okay. So what does this mean for information storage and processing on a quantum computer, right? So we said a classical bit is a choice. It's a 1 or a 0. But an electron doesn't have to make that choice. It doesn't have to be just a 1 or a 0. It can be anything in between. And there's many ways to be, to not choose to be exactly 1 or exactly 0. And in fact, the number of these ways turns out to be the same as the number of directions that you could point an arrow on the surface of a sphere. Okay. So there's many more choices for our electron or for our quantum bit than there are for a classical bit. And this is part of what makes quantum computers powerful, these more choices. But at this point, it is kind of natural to ask, well, if all I need is arrows, why don't I just build my computer out of classical arrows? This is something that people did think about back in the early days of computing, and it was called analog computing, okay? Seems like a really good idea. Turns out it's not qualitatively better than digital computing. So there must be something more to the story than just this large number of directions. What is it? To find out what it is, we're going to go back to this double slit experiment of the electron. And I'm going to say, look, my electron, it hits the screen. It's always a dot. It looks like a particle. I'm just going to look at which of those slits it goes through. And I'm going to catch it. Okay? We're going to figure out what's going on and how it's doing this wave thing that it's doing. So here's what I'm going to do to set up my experiment. I'm going to put a little camera beside each slit. And if the electron goes through the right slit, there's going to be some kind of flash on the right camera. I could call that my 1. And if the electron goes through the left slit, there's going to be a flash on the left camera. I could call that 0. Okay? So I go ahead and I do this experiment. And what I see is something very surprising, which is that this experiment now starts to look like just a coin toss, which is to say, some of the time the right camera flashes. Okay, oh, I switched my 0 and 1 on you. Okay, my right camera flashes. I could call that a 0. Okay, that's like a heads. Okay, some of the time my left camera flashes. That's a 1, or I could call it a tails. But what I find is I never see both of these detectors flash at once, okay? So when I look for the electron, when I watch it, I force it to choose. I take away its freedom to be the wave and do all the things, okay? And now it has to either go left or right. And when I do this and I look at the pattern that I see on the screen, I see a pattern that looks exactly as if that experiment was me throwing baseballs. Now, the way that I've described this so far, this seems like it would actually be really bad for quantum information, that as soon as you look at the system, everything looks random like a coin toss. But the key is that not all coin tosses are fair. So as my first grader told me yesterday, she said some of the kids in the class, they take that coin and they hold it with the heads up and they drop it. And then they know that it's going to come up heads, right? That's not 50-50 random. Now you know what the coin is going to be. And so they win every time. And electrons are like that, right? So we can flip our electron coin. When we make a measurement, we can set it up so that the measurement is going to be like a fair coin toss, 50-50, okay? But we can also set it up so that it's going to be like a very biased coin toss, so that with a very high probability, we're going to find either a 0, a heads, or a 1, a tails, okay? And so what this means is that while I'm not looking at my electron, while I'm running some kind of computation, it is free to explore this entire space of directions on the sphere, okay? But as long as I arrange things so that at the end, it's pretty close to pointing either in the 0 direction or in the 1 direction, When I measure it, I get digital precision. Okay? And this is the difference between a quantum bit and an analog classical bit, is I get this large space of things to explore, but when I actually go to read it out, I get, due to the funny way that these measurements work in quantum mechanics, I get digital precision. Okay. Now, if I want to build a quantum computer, I mean, having one quantum bit is great, but obviously I need a lot more than one quantum bit. And you might ask, is there anything else that is different in quantum mechanical systems, that I only start to know about when I have 2 or more quantum bits, 2 or more electrons? And the answer is yes, which was phrased in a way that I really like by one of the giants of kind of quantum materials of the 20th century, Phil Anderson, who famously said, more is different. And this is very, very true in quantum mechanical systems. And I want to show that to you by talking about another experiment that we could do. Okay? So now I'm going to stop saying electrons. I'm going to call these quantum coins, right? But basically it's something that when we measure it is either going to be 0 or 1, and can be in a superposition, can be free to be wave-like when we're not looking at it. Okay? So here's my experiment. So my friend Chen has the ability to prepare pairs of quantum coins and prepare them in a very special way. We'll talk about what is special in a minute. And Chen is going to take these pairs and put them in little boxes, and one box is going to get shipped to Alice in Los Angeles, and the other box is going to get shipped to Bob in New York. Okay? And when Alice and Bob get their boxes, they're going to open them in one of 2 ways. So this box comes and you can either open it on the top, and you're going to see heads or tails, or you can open it from the side, and you're also going to see heads or tails. But the answer that you get if you open it on the side is not necessarily the answer that you get if you open it on the top. And crucially, once you open it at the top, you can no longer access this information that you would have had when you open it on the side. So there's 2 ways of opening the box. They are different, and you can only do one of them. Great. So Chen and Alice and Bob get together, and they start doing this experiment, and Chen starts sending out these coins, and Alice and Bob start getting them, and they start opening their boxes, and they look at what they get. Okay? And they notice the following things. So first of all, Alice by herself, she's recording her results, and she sees heads, tails, heads, heads, tails, tails, heads, tails, right? She sees something where her set of coins really looks like every time she's just flipping a classical coin. There is nothing about her data in isolation that tells her that there's anything quantum mechanical at all about her system. There's no information. It's completely random. Okay? And the other thing to notice about this sequence, so in this sequence that we looked at here, they're opening different boxes. Okay? And when they open different boxes, they also don't notice any particular pattern in the results. Sometimes they get the same thing, sometimes they get different things. So then, Alice calls up Bob, and she says, hey, let's try something. Let's try opening the box in the same way every time. So they do. Okay? And they try it, 100,000 times. Okay? We're not going to do it 100,000 times here. And they notice a third thing, which is that in spite of the fact that their individual measurements, that they see look like totally random coin tosses, right? So Alice is like, oh, mine still looks random. Bob is like, mine still looks random. But when they talk to each other on the phone, they're like, holy smokes, every time we got the same thing. Every single time. And this, which is something that we can only see when we have 2 or more quantum particles, is called entanglement. And that's what we call it now. And it's this fact that you can have processes which our theory of quantum mechanics tells us are totally random, and they're happening in very far away places with no way for these coins to talk to each other, and yet they know to always be the same thing. Now, the original name for this phenomenon, which was due to Albert Einstein, was spooky action at a distance. Okay? And Einstein thought that this was very spooky, because he's like, well, how do they know if it really is random, when Alice opens the box on top, if it really is random whether she sees a heads or a tails, and Bob's is similarly random, like, how do those coins know to be doing the same thing? Right? It's as if they're connected by this invisible string. So this really bothered Einstein, and his resolution to this was that quantum mechanics, as it was understood in the early 20th century, when he was thinking about this, was wrong, or at least it was incomplete. There was something missing about the way that we were describing what happens when we look at quantum systems. And Einstein worked for a long time on this purely theoretically, but one of the beautiful things about physics is that it's actually a science, right? And rather than bringing our biases about how the world should work to bear, ultimately science is about making hypotheses about how the world works and then testing them. And in the 1950s, John Bell came along and identified a very clever test that you can do to ask whether indeed this entanglement, this spooky action at a distance, is what nature is doing, or whether Einstein was right and quantum mechanics, as it is described, is missing something. And to make a long story short, this took like 60 years to do these experiments. They were very hard. There was a lot of technology that was developed. This won the 2022 Nobel Prize in Physics, the technological developments that led to these experiments being able to be done. But the ultimate answer, right, by our 3 Nobel Prize winners is this too weird to be real? Nope, nope, okay? We now have very convincing experimental evidence that this spooky action at a distance is really what these quantum mechanical systems are doing. And I don't have time to say much about the experiments, but I just wanted to put this picture up here. This is like a kind of satellite photo of the experimental apparatus. And basically, they had to make these pairs of quantum particles in their little boxes. And it's really, really important, when you do these experiments, it's really important that you have to know that the particles couldn't secretly be talking to each other. Okay? Which means you have to be able to do the measurements essentially at the same time, okay? Faster than light could go from one to the other, and so this is why they had to be able to send them like over distance of, order a kilometer to really make this convincing. Okay, beautiful experiments. So, to summarize, how is quantum mechanics different from classical mechanics? Well, we've talked about 2 things. We've talked about this phenomenon of superposition. A quantum particle, an electron, is free to be a wave. It's free to do all the things, explore all the paths until you look at it, and then it's got to settle down and do one or the other, okay? And entanglement, right? This spooky action at a distance. How does the left hand know what the right hand is doing? And from the point of view of information, entanglement, I think the right way to think about this is the whole of the 2 particles together has a lot more information than the sum of its parts. Okay. Good. So that brings me to part 2. So that's the essence of how quantum mechanics plays a role in computing. And so now we're ready to talk about what quantum computers are good at. And I want to open this section by quoting Richard Feynman, who famously said, if you think you understand quantum mechanics, you don't understand quantum mechanics. Okay. Now, I think that when he said this, he really meant like these phenomena, superposition and entanglement, are so weird and so counterintuitive that there's no way to really feel like you understand what's going on. But another thing that he was thinking about a lot as well is that in order to kind of really understand quantum systems, we might be able to simulate, we might want to be able to simulate them, okay? And that these phenomena of superposition and entanglement actually make quantum systems with lots of particles very hard to simulate on a classical computer, okay? And the basic idea here that you should have in your mind is this business of the whole being more than the sum of its parts. Because the way that information is stored in this computer here that I'm using to run the slideshow is in just an array of like 1s and 0s, okay? It's like a string of 1s and 0s, a string of bits. And that string of bits can never be more than the sum of its parts. That's just what it is, right? But if I have, a string of 1,000,000 bits, It is the sum of its parts. If I have a string of 1,000,000 qubits, it can be way, way, way more than the sum of its parts in terms of the information content. And this is essentially, so this entanglement is essentially what makes it really, really hard to effectively simulate quantum systems with lots of particles in them on a classical computer. And so Feynman reasoned, well, if quantum systems are hard to simulate classically, but like they're quantum systems, they're doing their quantum thing, so surely they should be good at simulating themselves, right? So there must be things that a quantum computer made out of quantum bits could do that would be hard for a classical computer. And this was, I think, one of these examples of like a super appealing, intuitive sounding idea that then had a lot of people scratching their heads for a long time to be like, but what exactly should we do? So Feynman was talking about this in the early 1980s. It took order 15 years before the first clear case of a quantum algorithm, so something that you can run on a quantum computer, which performs much better than what, certainly what we can do right now on classical computers, okay? The first example of such an algorithm was in 1994 due to Peter Shor, okay? And Peter Shor's quantum algorithm tells us how to use a quantum computer to factor numbers. So just, a primer, what is factoring? Factoring means I'm going to give you a number, and I'm going to kind of break it up into its components. So it's like 49 is 7 times 7. Why do I stop at 7? Because 7 is what we call a prime number. That means that it can't be divided by anything except 1 in itself. So you're like, cool, I learned how to multiply and divide in elementary school, so that doesn't seem that impressive. So we'll add some more factors. So I think most of you could factor 49, okay? Less of you would be able to tell me the prime factors of 147, which turn out to be 3 times 7 times 7, right? And I could keep going, right? I could make bigger and bigger numbers by multiplying together more and more of these prime factors. And the bigger the number gets, the harder it gets. You can just sort of see this intuitively. The harder it gets for you to tell me what those factors are. And by the time we get to playing the game where I'm giving you like 10 to 15 digit numbers, this problem is hard, not just like, oh, I don't know how to do that hard, like we don't have any algorithm on a classical computer that can do this in any reasonable amount of time, okay? And Shor showed that if you have a quantum computer, this is not true. You can factor very large numbers in a pretty reasonable amount of time. So this was really important for the history of the development of quantum computing for 2 reasons. First of all, finally there was at least one example of something that a quantum computer could do and could do much, much better than a classical computer. So this is very intellectually significant. But it was also important in another way. So you might be like, factoring large numbers, well, that's okay, cool, that's for the people who really love numbers. But it's also important for all of us because the fact that it's hard to factor large numbers is the basis of the standard encryption schemes that were used for much of the history of the internet to do encryption. So Shor's algorithm got the attention not only of scientists and mathematicians and computer scientists, but also of national governments, funding agencies, things like the US Department of Defense, because it was, sort of everyone suddenly said, well, we don't want to be the people who are last to the game in developing this quantum technology if it allows, other countries to decrypt a lot of important secrets that we might want to keep private. Okay, and so this was, something that started to infuse a lot of money into doing the basic development work that has ultimately led to the quantum computers that we have today. All right, now that said, it is not the case that, I think most people believe that factoring large numbers is going to be the biggest impact, application of quantum computers today. For two reasons. First of all, we've now had like 40 years to see this coming, and so there are other ways to encrypt data on the internet. So you should not be panicking that when the quantum computers come, all of my bank accounts are going to be hacked. Okay. But also because actually, like running Shor's algorithm sets you have to have a really, really good quantum computer, okay, to do this. This is a very high bar, and the machines that we have today are not there yet. And so, in brief, there's other applications that are probably much closer to what Feynman originally had in mind, particularly in chemistry-related fields, where there's a lot of optimism that quantum computers might really, in the near term, be able to do things that classical computers cannot. And again, chemistry is something with a lot of very important real-world applications. Things like what we call catalysis helps us make manufacturing processes more efficient. So if you can find better catalysts, you can bring down the energy and money costs of a lot of important processes. And people often point to drug discovery, which again, if you could predict what these big and complicated molecules were doing, this would save a lot of money in basic research and development. These are the kinds of applications that people are more thinking about now. And I would say, right now, it's maybe not clear like exactly what the status of quantum computers versus classical computers are. And you might find that, with regards to these problems, you might find that confusing because you might have seen some headlines like this, right? These appear every so often. This machine can solve problems in seconds that used to take years. This machine did in minutes, something that would take billions of years for the world's fastest supercomputer, right? And some of you may have seen these kinds of claims, and they do appear from time to time. And so I also want to talk a little bit about what are these tasks, okay? These tasks where you see these claims that a quantum computer really is doing something fantastically better than a classical computer, okay? So these tasks are what we call benchmarks. Okay? And the idea here is the following. Before going out and discovering new drugs and bringing down the energy cost of making fertilizer and all of these important things, the first thing that you might want to do is, because those problems are kind of hard, okay, and maybe we don't have great algorithms for all of them. The first thing that we might want to do is identify a task, even if it's not a task that is very useful, okay, a task where you can show that your quantum computer is demonstrably, irrefutably better than any classical computer on the planet, okay? And so these are what we call benchmarks. These tasks are, they're not useful tasks. In fact, they're quite useless tasks. But they're chosen because they're things that the quantum computer kind of does natively, and because they happen to be things where we can prove that if you had a perfect quantum computer, a classical computer could not do this anywhere near as well as your quantum computer could. Okay. And on these problems, there's been, a lot of these impressive headlines, and I would say a lot of progress. But even so, the other thing that maybe doesn't make the cover of Time magazine for sure, right, is there's also a long history of these claims being made where it's like, hey, we did it in like 5 minutes, and it would have taken 1,000 years. And then maybe a little bit in the news background, somebody comes along a few years later, and they're like, actually, we came up with a clever way of doing this on our classical computer, and that 1,000 years is actually only 15 seconds, so. Okay, and so that's what these kind of headlines are. Now, so in other words, there's a long history of these claims getting made, and many of them being debunked. Now, I should add here that there are claims that that were made in kind of 2024, 2025 by Google and by a group in China that have not yet been debunked, and I think it's not yet clear whether they will be. In other words, I think a lot of people believe that we are close to this point, and we may have passed this point with these benchmarks, where quantum computers really can outperform the classical machines. But, okay, so that's exciting. But I do want to talk a little bit with this debunking issue about the third thing, which is like, well, wait, what went wrong? Because I told you that this is something where I can prove that it's hard for a classical computer to do as well as a perfect quantum computer, okay? So what went wrong is that the quantum computers that were running these experiments, especially the early experiments, I mean, they're not perfect. And essentially, the exploit that these clever people who came up with these classical algorithms used was they exploited the fact that these quantum computers, maybe they weren't quantum enough to beat the classical machines. So in the last part of my talk, I want to talk a little bit about why is it hard to be quantum enough, which I think will help us appreciate why is it so hard to build a really good quantum computer. And so I want to talk about this in the context of another famous paradox of quantum mechanics, which is called Schrödinger's cat. So Schrödinger took his beloved pet cat and sealed it in a box with some radioactive material. Maybe here I'll use my pointer. Some radioactive material in this box, a detector which will detect radioactive decay, okay? And that detector is connected to this hammer so that if a radioactive decay occurs, the hammer is going to smash open the bottle of poison and Kitty's going to die. And for us, right, we can think of this radioactive substance as like our electron choosing to go left or right, choosing a 1 or a 0. And because this detector is here, right, we're going to sort of correlate if the electron was like a 1, the cat is going to live, and if the electron is like a 0, the cat is going to die. Now, classically, right, if what was in the box was a baseball and not an electron, then I know that the cat it's either alive or it's dead. I don't know which until I open the box, but it's definitely one or the other, and it's not both. But what quantum mechanics tells us, basically, is that if the electron is doing both of these things at once, if the electron is in this superposition, and you assume that quantum mechanics also applies to things on the scale of cats, okay, yeah, it is kind of funny, then the cat is in this superposition, just like the electron. The cat is free to be both alive and dead at once, okay? And Schrödinger used this experiment to kind of show how counterintuitive quantum mechanics is, how ridiculous this seems when we apply it to the scale of cats. But I want to use this experiment to talk about a slightly different thing, okay? Which is, so what happens when we open the box? So we said that the electron is free. It's free to be a wave until we look at it. And similarly, if we think that quantum mechanics applies to the whole system, right, of our electron and our cat and the bottle of poison and the whole thing, then the cat is free to be both alive and dead until you look at it, okay? But when you look at it, right, then we force it to choose. So when we open the box, Kitty's either going to live or Kitty's going to die. And this also seems kind of weird, because you're like, what's special about me, right? So the question here is, who killed Schrödinger's cat, right? And the puzzle is really, who has to look at the cat? Who has to see the cat in order for it to be killed, right? And it kind of feels like this is one of these, oh, if a tree falls in the forest and there's no one to hear the sound kind of questions, right? And you can definitely go down that path. But actually, from the point of view of how we understand quantum mechanics, there's a fairly clear answer, pragmatically speaking, that applies to all of the experiments that we can do, which is that anything that can take information out of the box about whether Kitty is alive or dead starts to make the cat have to decide a little bit, right? So if you open the box and just look at it, it's definitely alive or dead. But any information that leaks out makes this cat a little bit less quantum, okay? And so this, I think, is a useful way to think about what is the challenge of building a quantum computer. So let's think about what we're trying to do. We've got all of our quantum coins, our little boxes here, our quantum boxes, And we want them all to be operating together in this quantum way. And if we want them to keep their quantumness, whatever that means, it's very, very important that we set this up in such a way that essentially no information about what this system is doing, what state it's in, is leaking out into the outside world, right? So we have to have it really, really, really well isolated. Okay, so we have quantum systems that we can isolate really, really, really well. But the problem is, if you isolate it completely, how are you going to compute, right? I mean, I can have a great system, but if I can't manipulate it in time with very high precision, I can't compute with it. And so this is just an incredibly difficult task to have the ability to put in all of these controls to manipulate the individual components while still keeping this system incredibly well isolated from the outside world so that it keeps its quantumness. And at this point, you might start to worry, is this so hard that it's just impossible to build a quantum computer, kind of on principle? And there's a sense in which if you try to build a quantum computer only by getting your best engineers and making the hardware better and better and better, there's a sense in which the answer is yes. That there's a limit of how much quantumness we can get on engineering alone. Okay? And this is essentially why our current quantum computers are not perfect quantum computers. And what I mean by that is there's only so many of these qubits or so many of these quantum boxes that I can keep really quantum, and there's only so much time that I can really keep them quantum for, right? And basically, in order to best your classical computer, what the engineers are doing and what the latest round of hardware improvements have done that maybe have attained that bar is just making this number and this time bigger, right? But kind of fundamentally, we don't think that we can keep on making it bigger and bigger, better forever. The hardware game alone is not enough. And the current machines that we have are not good enough, for example, to run Shor's algorithm. But like I said, I think many people believe that they may have now surpassed this benchmark test. But luckily, okay, we can get past this seemingly distressing obstacle by using clever software. So actually, this is something that, in the early days of classical computing, right, also the hardware was pretty faulty. And so people, to get good results, people also thought, well, how do you basically essentially use software to get around these faults, the fact that the hardware is not perfect? And we know that we can also do that for quantum computers, that if we can get this hardware good enough, then we can use software to get the rest of the way and really ultimately get towards this extremely high-performing quantum computer that could really do these tasks that are extraordinarily difficult for classical machines. And the really exciting thing is that there's been a bunch of experiments released in the last couple of years that show that the current very best quantum machines are really, are approaching and maybe again have surpassed these hardware requirements for having the capacity to run this software. So, we're definitely at least the first step down that road. Good. And so I want to just sort of, leave you with a couple of thoughts, to kind of summarize. And I want to look both forward and back. So, I've talked about quantum computers, but I also, in this talk, inevitably spend a bunch of time talking about how the quantum world is strange and sneaky and deeply counterintuitive. And it really has been a century of basic research to bring us to the level of understanding that we have today, which is what we needed to build these amazing quantum computing machines. And I think it's worth noting that for most of that century, most of this research was not research that people were doing, necessarily with a clear application or goal, but it was research that was really driven by human curiosity, which is a very beautiful thing. People just found these systems so puzzling, so interesting, that they wanted to learn more about them and how they worked. And ultimately, that human curiosity, as often happens in science, has led to the kinds of technological breakthroughs that maybe you wouldn't have had if people hadn't followed that curiosity-driven path. And so I think that's a wonderful story about how our desire to understand the world around us brings not only understanding, but potentially other benefits down the road. And then looking forward, I think we are at a really, really exciting time in our understanding of quantum computers, but also just quantum many-body systems, because quantum mechanics is very fragile, and it's very fragile in large systems. And we are just now beginning to have the kinds of machines that allow us to really explore this frontier of quantum systems with many particles that we can manipulate in time. And so, as well as being potentially useful for applications, I think there's a whole new world of exciting things for people to explore going forward. And I will end there, and I think we have some time for questions.
We have time for questions.
Is there a future in which quantum computing can be used in lieu of the traditional data centers we're using today, in which the energy and water intensive load is reduced?
Yeah, good. So the question was, is there a scenario where we could sort of replace existing data centers with quantum computers? I think. So the first thing, in terms of energy load, the first thing that I should note is that these actual quantum machines, to keep quantumness, one of the things that you need to do is make your system very, very cold. So to operate a quantum computer is actually energetically expensive. So that's kind of the first caveat. The second caveat is, I think that who knows what's going to happen in 100 years' time? Like, I certainly don't. But what people are envisioning, more on a kind of maybe 10-year time scale, is that you're going to have a problem. So one of these problems in chemistry, okay? And chemistry is a big subject. There's a lot of people who've been working for a very long time on classical simulation methods. And basically, the idea is that probably in the near term, what we're going to be doing with these quantum computers is using them in conjunction with our best classical methods to kind of solve that last mile problem. What's that little bit that you really can't do on your classical hardware? So in terms of quantum-only data centers and stuff like that, like I said, I don't know what things will look like on the long term, but in the short term, I don't see that as being kind of the main way forward. Yeah.
At some point, you have your qubits in there, and then you're going to get some sort of answer that you're looking for. What are the steps? Can you describe the steps, like going from all this quantum thing that's going on inside the box to I really want the factors of 39, not the factors of 15. What are the steps in between? Because something has to get physical. And
yeah. Okay. So let me say that. So I don't want to try and explain in detail Shor's algorithm specifically, because this is like an entire long chapter in the standard quantum computing textbook. But
another hour lecture, right?
Yeah. But maybe let me say the following thing. So I think you've touched on an important point, right? Which is that during this computation, so an essential part of Shor's algorithm is, first of all, you have to take your factoring problem and you have to ask it in the right way. And that's actually, maybe something that I can't get into without going into too much detail. I have to figure out how to ask it in the right way. Now, during this computation, in the middle, my system is in this really complicated superposition, okay? So if I wrote it out as bit strings, I would have millions, billions of bit strings all in this superposition. And basically what the quantum computer can do by making this superposition of bit strings is it can do things in parallel in a way that a classical computer cannot, okay? That's the power of the quantum computer. The challenge is that if I want to get my digital readout, I have to then, before I measure, I have to cleverly get the information out of the superposition. And that's actually what's hard. And so, essentially, the magic of Shor's algorithm and certain other applications, there's many things that you can do in parallel. But it's very difficult to get the information out. And the magic of Shor's algorithm is that you can find a clever thing that you do to your quantum system at the end that allows you to move all of that superposition back onto a single bit string, which you can then read out by measurement. Hopefully that gives some answer. Yeah?
How would you recommend one becomes a researcher of quantum computing in a professional capacity?
OK, yeah, great question. So I would say that depends a bit on where you are in your kind of educational trajectory. So quantum computing is somewhat interdisciplinary. And I think that the way that, for example, computer scientists approach these problems is quite different from the way that physicists approach these problems. But I would say that most people who work in the field have a bachelor's degree either in physics or maybe sometimes chemistry. I think there may be a time where there's more demand for people with bachelor's degrees. There are master's programs. But I think right now, a lot of the people who are getting hired into the workforce do actually come from PhD programs. And I want to say, for the young people in the audience, because there's a common misconception that people have, they're like, oh, I can't afford to do a PhD because that's going to be like 5 more years of school and I can't pay for it. And so you should all know, all you young people, that a PhD, a doctorate, is something where if you come to the University of Minnesota, to any other major American school, we do cover your tuition and we give you, not a big salary, but we do give you a salary so that you can live. So you're not going into debt. And so if you're really excited about research and you're kind of at that point in your educational trajectory, I encourage you to look into those options.
Other question?
Could you talk about entanglement a bit more? Because it seems to me like if you know the state of the one particle, you should know the other one. So that seems like information lost.
OK, so let me make sure. So let me make sure that I understand the question. So the statement about information is this: when Alice is doing her measurement by herself, she sees only a coin toss. A coin toss is totally random. There's no information in that. When Bob is doing his measurements by himself, same thing, OK? But when they talk to each other, right, they see that actually it's not that there's no information in the system as a whole, right? Because there is the information that Alice knows that once she's done her experiment, right, if Bob measured in the same way, she knows what he's going to get. So that's where the information is. Now, there's a subtlety here. So, you might think, oh, but, what if Chen was sort of, preparing these where he's like, well, they're both going to be heads or they're both going to be tails. And then you'd be like, well, that's a classical way of making these perfect correlations. And so the subtlety, which I didn't say much about, is it's important that you can open these boxes in 2 different ways, OK? And because you can open them in 2 different ways, you can actually show that there is no classical random process that can give the same set of joint measurement outcomes as Alice and Bob. So these are called Bell inequalities. There's fantastic, lots of fantastic places you can read about it on the internet that go into quite a bit more detail if you're interested. Yeah.
I also kind of had a question on the entanglement. So if Chen also had a friend, Sue, and was sending her these quantum boxes as well, if she was opening them, would she get the same results as Alice? And so she thinks they're random, and then when she compares with Alice and Bob, would she get the same results, or does it kind of fall apart beyond 2 quantum bits?
OK, so great question. So this depends a little bit how Chen is preparing these things. But there is a way for Chen to prepare 3 quantum bits, or in fact 4 or 5. These are often called cat states, actually, after Schrödinger's cat in the literature. Okay, but there is a way for him to prepare them such that they each will individually see something random, but they'll see perfect correlation. So they're all going to get the same thing.
Okay, so in the Schrödinger's cat Schrodinger's cat scenario, when photons, when you need to like see or detect the outcome, you need like photons, and to feel it, you need to like touch it directly. Is that the thing that reduces the quantumness of?
Yeah. So in some sense, yes. But I think the important thing is like, and in the history of quantum mechanics, there are a lot of people who are like, well, like, what is it? What is it that makes the electron choose? Is there a conscious observer? Is there some size? Okay, so there is a real question here. But pragmatically speaking, when we do physics experiments, everything is consistent with the fact that I don't have to look at those photons, okay? Once those photons are out of the box, the secret is out. And it's not that they have to be detected or observed, it's just that the information is out in the world, and that's enough to make your cat less quantum. And that's what we see in these experiments is, basically, photonic quantum computers, and when those photons are lost, that makes the system less quantum, for example, to be very concrete.
Yeah. Okay.
I have a follow-on question to that one. And I have a background as a synthetic and organic chemist, so I'm going to probably sound like I'm asking a chemistry question. I can definitely imagine a way of building a nanoparticle or metal organic framework or something where you've trapped your quantum thingy inside this container. It strikes me, though, that you can never actually open the box. You have to look at the box without opening the box. In a physical sense, you can't open the box. You have to detect, you have to look, you have to metaphorically open the box by using spectroscopy, spin flip, radioactive something. Can you comment?
Yeah. So actually, this touches on something that was much discussed in the early days of quantum mechanics about this question of like what makes the electron choose, and then we call this collapsing the wave function.
What is a measurement?
Yeah, and you've hit on a really crucial point, which is like, so when I look at a baseball, what's actually happening, right? Is there are photons, there's light that's bouncing off this baseball that's coming into my eye, but the light is like really tiny compared to the baseball. So we don't even think about this. We're like, yeah, the ball's moving. It doesn't matter. If I turn the lights on, it doesn't slow down or change direction. But an electron is super tiny. And so actually for that electron, it's like, I remember in high school one time I was on a backpacking trip and our teachers were telling us put all the food away. And the teacher was like, if you're a mouse, one crumb of food is actually like a whole buffet, okay? So if you're an electron, a single photon is actually a big deal, and it bumps into you, and it really kind of changes what's going on. And so that's, I think, a very useful way to think about why measuring a quantum system is so disruptive. It really changes the whole future plan of that electron, right? It was gonna be in a superposition, I don't know, physics, chemistry, and I was like, okay, forced it to choose.
Biology.
I was going to say physics.
I think discussions about Schrodinger's cat will definitely could go on all night. Let's thank our speaker again. And I just want to point out that if you want to learn more about quantum entanglement, I suggest that you go to your local comic book shop and get Justice League of America number 19. In this story, the Atom is talking about saying, listen up. Last year, quantum physicists ran a groundbreaking experiment. Working on a subatomic level, they divided a photon, a light particle, only to discover that whatever alterations they made in one half were instantaneously mirrored in the other half 6 miles away, even though there was no physical way for the two halves to communicate with one another. So, and I actually met the writer of this comic book. I said, where do you get these ideas? And he turns out he got it from Physical Review Letters. Actually, there were New York Times articles about this when it came out. And one of the co-authors, you see the last author, Anton Zeilinger, and this is the same Zeilinger that Professor Burnell mentioned, who shared the Nobel Prize for these quantum entanglement groundbreaking experiments. So what's next? Unfortunately, a tunnel through nothing. We've had this, brain-busting quantum entanglement, and now we're not going to necessarily entangle, we're just going to use it to walk through walls. And I'll describe this, and this is a real thing. So I'll talk about that next week. And I would encourage you to join our mailing list. And that way you'll be registered, and we're going to be sending, this way you get to also help pick our topics for next year. And I would like to thank Professor Burnell again. And if you'd like to support us. Now, I've kind of run out of books, but I know that once I start giving you a little bit of swag, I know that it's very hard to not feed the beast. So, so we have here coffee mugs from the William I. Fine Theoretical Physics Institute at the University of Minnesota in the School of Physics and Astronomy. And we have 3 of these mugs. So look underneath your seat. And if you see a Quirky Quantum golden ticket, okay. And with that, I want to thank everyone. I want to thank you all for coming, and I'll see you all next week.